Welcome to the another example. The example 5. A pulley is geared to a shaft midway between two bearings. The shaft is made of cold drawn steel, for which the ultimate tensile strength is 550 megapascal and the yield strength is 400 megapascal. The bending moment at the pulley varies from minus 150 Newton meter to plus 400 Newton meter. The torque on the shaft varies from minus 50 Newton meter to plus 150 Newton meter. Obtain the diameter of the shaft for an indefinite life. The stress concentration factors for the key way at the pulley in bending and torsion are 1.6 and 1.3 respectively. Take the following values: factor of safety 1.5, load correction factor 1.0 in bending and 0.6 in torsion. The size factor is 0.85 and surface finish factor is 0.88. So these are the given data. Ultimate strength is 550 Newton per mm square. Yield point strength is 400 Newton per mm square. Minimum bending moment minus 150, maximum bending moment plus 400. And the torque minimum is minus 50 and maximum is 150 Newton meter. And the fatigue stress concentration factor in bending is 1.6 and fatigue stress concentration factor in shear is 1.3. Factor of safety is 1.5 and the factors given as KB is 1 and KS is 0.6. Size factor and surface finish factors are given. Let us find out the diameter D, which is the diameter of the shaft in millimeters. First of all, let us consider the equivalent normal stress due to bending. The maximum bending moment and minimum bending moment are given as 400 and minus 150. The average of these two is 250 by 2, 125. And the variability in this plus 400 to minus 150, the variability is 400 minus of minus 150, that is 550 divided by 2. The variable bending moment is 275 Newton meter or 275 into 10 power 3 Newton mm. The section modulus is pi by 32 d cube, that is 0.0982 d cube. The mean bending stress, the mean bending moment divided by the section modulus 0.0982 d cube, and it is 1273 into 10 power 3 by d cube. Variable bending stress is mv, that is variable bending moment 275 into 10 power 3 divided by the section modulus 0.0982 d cube. So one is 1273 divided by d cube and another is 2800 by d cube. The endurance limit in reverse bending is half of the ultimate strength. So that is 550 by 2 is 275 Newton per mm square. Since there is no reversed axial loading and the whatever that is applied, that is the bending stress is causing the normal equivalent stress. So normal equivalent stress is bending stress here, that is sigma m plus sigma v by sigma e in bending multiplied by the yield point and factor of safety, the fatigue stress concentration factor in bending, and in the denominator we have the two factors, surface finish and size factors. 1273 into 10 power 3 by d cube plus 2800 into 10 power 3 into 400, 1.6 by d cube, 275.88 and 0.85. So after calculating this, it comes out as 9889985 into 10 power 3 by d cube Newton per mm square. So this is the normal equivalent stress. Similarly, we will find out the equivalent shear stress. For that, the two moments given, the average of these two is 50 and the variability of these two is 100, and the mean shear is from the mean torque, and that is 16 by pi d cube into 50 into 10 power 3, and the variable shear is 16 by pi d cube into the variable torque 100 Newton per mm square, that is 100 into 10 power 3 Newton per Newton mm rather. So 100 is the Newton meter and 100 into 10 power 3 is Newton mm. So Newton mm divided by mm cube, that comes out Newton per mm square. So here the things you require: The endurance for the shear loading is 50%, rather here 0.6 factor is given. So endurance limit in the normal is 275. For the reverse torsional or shear loading is 0.6 of that is 165, and the yield strength in shear is equal to 50% of the normal yield point. The yield point in the normal direction is 400, and in the shear it is 50% of that, which is 200. So let us take all these things for the equivalent shear. So tau m, that is 255 by d cube into 10 power 3, and tau e is 510 by d cube into 10 power 3, and tau y is 200, and fatigue stress concentration in shear is 1.3. Surface finish and size factors are given as 0.88 and 0.85. So now this is total 1329 into 10 power 3 by d cube. Now the maximum equivalent shear is yield point in shear by factor of safety. Yield point is 200, and factor of safety is 1.5. That is on the left hand side, and right hand side it is either 1 by 2 outside the root, or when take the 1 by 2 inside, that is tau ne by 2 whole square plus tau square. So tau ne is that is here 99985 into 10 power 3 by d cube into 2 whole square, and this is 1329 by d cube into 10 cube. So now a common thing in these two is d cube. So there is square and there is root. You can take it outside, that is 1 by d cube, and by simplifying the numerical values here, that is 5165 into 10 power 3. So now 5165 into 10 power 3 by d cube is equal to 200 by 1.5. Now we calculate the d value as 33.84 mm. Approximate standard value is, nearest standard value is 35 mm. The diameter of the shaft is 35 mm. Let us move to one more example here. A centrifugal blower rotates at 600 rpm. A belt drive used to connect the blower to a 15 kilowatt and 1750 rpm electric motor. The belt forces a torque of 200 Newton meter and a force of 2500 Newton on the shaft. The figure shows the location of the bearings, steps in the shaft, and the plane in which the resultant belt force and torque act. The ratio of journal diameter to the overhung shaft diameter is 1.2, and the radius of the fillet is 1/10 of the overhung shaft diameter. Find the shaft diameter, journal diameter, radius of the fillet to have a factor of safety 3. The blower shaft is to be machined from hot rolled steel having the following values of stresses: endurance 180, yield point 300, ultimate tensile stress is 450 MPa. The given values which are useful, the torque is 250 Newton meter, that is 250 into 10 power 3 Newton mm, and the forces applied 2500 Newton, factor of safety is 3. Endurance, yield point, and ultimate stresses are 180, 300, and 450 Newton per mm square respectively. Here you can see the load applied approximately at the center, and from the center to the point it is given as 100 mm, and from this point at the end of the bearing you have 25 mm. So there is a from the load to this point it is 75 mm, and there is a load of 2500 Newton. So capital D is the journal diameter and small d is the shaft diameter. R is the fillet radius. Ratio of journal diameter to the shaft diameter, capital D by small d, is 1.2, and radius of the fillet is 1/10 of the shaft diameter, that is 0.1d. So hence you can take it as R by D is equal to 0.1. So D by D is 1.2 and R by D is 0.1. The theoretical stress concentration factor is 1.62. The 2 points at which the failure may occur or at the end of the keyway and the shoulder fillet. The critical section will be the one with a larger product of Kf into m, since notch sensitivity factor Q is dependent upon the unknown dimensions of the notch, since the curves for the notch sensitivity factor are not applicable to the keyways. Therefore, the product of Kt into m shall be the basis of comparison of two sections. The bending moment at the end of the keyway is Kt into m. Kt is 1.6 and this is 2500 into 100 minus 25 plus 10. So you can see it here in the diagram, 100 minus 25 and this is another 10. So now between this point and the load application point, so you have 65. So that is 100 minus 35, 65 into 500 into 1.6, that comes around 260 into 10 power 3 Newton meter. Then the bending moment at the shoulder is Kt into m. Kt is given as 1.62 and moment is 2500 into 100 minus 25, that is at the shoulder fillet. The Kt into m at the shoulder fillet is large. Out of these two, this is 260 into 10 power 3, this is 303 750 Newton mm, and this is 260 into 10 power 3, and hence out of these two, this seems to be a larger one, and Kt into m is the shoulder fillet. Therefore, consisting the shoulder fillet at the critical section, we know that the tau yield point by factor of safety is equal to the equivalent shear stress, that is pi by 16 by pi d cube into square root of sigma y by sigma e into kf into m whole square plus tau square. So this is all the normal stress factor, and this is the torsional shear stress factor, and 16 by pi d cube into this is sigma y is 300 and sigma e is 180, and the kf into m is here you can see 260 rather, yes, you can see here, that is 303 750, and the second one is tau. Tau is given as how much tau? 250 into 10 power 3, you can see here, this is so 250 into 10 power 3, that is torque applied, and the bending moment applied over here is sigma y by sigma e into kf. Sigma y is 300 and sigma is 180, the kf into m is, that is 303 into 750. And the relation between yield point in normal direction to the yield point in shear is 50%, so that is 300 into 0.5 divided by factor of 33. Now we calculate the diameter of the shaft as 38.6 and nearest standard value is 40 mm. Once again we will go through this. So here you have the description of the problem, and this is the shaft, and which is supported at the end points as bearings, and the load is applied here at a distance of 100 minus 25, that is 75, and this is another minus 5, that is 65 mm distance, and with this you will have the bending moment as well as in the there is torque of 250 Newton meter, that is Newton mm. So this is the torque and this is the moment subjected to the fatigue concentration factor, and with these two we calculate the diameter of the shaft as 38.6, which is approximately 40 mm. So with this we come to an end as far as various varieties of problems in the unit number 2, and in the unit number 2 if we take a recap of that, first of all, we started with what is fatigue and what causes fatigue, and the variability factor is much more important, and hence the variability factor is much more in the completely reversed and cyclically reversed cases, and there are other types, reversed axial loading and reversed bending, and cyclically reversed like shafts which are carrying loads. So the endurance limit is the one. The higher the endurance limit, the member is going to resist the fatigue failure, and the endurance limit depends upon the various factors like surface finish factor and size factor, reliability factor, etc. So these are going to discount the endurance limit. And then the stress concentration, when the member consists of any surface irregularities like holes, notches, keyways, etc., they causes stress concentration. In order to reduce the stress concentration, we have to put additional holes or slots to make it uniform. So in that way you can reduce or uniformly distribute the stress concentration, so that it is not focused at one point, and hence it is distributed among the various locations on the shaft or in the rod. So therefore that way you can avoid stress concentration. And then for the definite life and for the indefinite life we use various applications. And in the definite life we use the SN curve, and with the help of SN curve we find out the dimensions of the member, or for the given dimensions of the member we can find out the life. S stands for stress and N stands for number of cycles of operations. And when you go for indefinite life, we use the Soderberg equation or the Goodman's equation. The Soderberg equation takes care of the ductile materials, and the Goodman's is suitable for the brittle materials. And there is a modified Goodman's equation, and the Goodman's relation is not taking care properly when it is subjected to combined loading conditions, and therefore in order to overcome the difficulties faced in the combined loading conditions, we use the modified Goodman's equation. So with this we come to an end as far as the recap of the unit number 2. I hope we were able to cater you with all the details with clear explanation, and hope you might have enjoyed the learning experience. Thank you very much.